So what I want to do now is that I want to look at some problem-solving strategies and then look at some examples of how we can apply it. So in this problem-solving strategies for energy, it says here that the first step that you should do is that you should identify two states of the system, two energy states, where one state is known and the other is an unknown. What do I mean by that statement? One state, you know everything about the energies, and in the other state, you don't know one thing about those energies. So what that allows you to do here is that you then set up a problem where you could then determine the position, that is the height or the compression, or the speed at that point. Once you've identified those two energy states, we go to step 2. For each state, then identify all the kinetic and potential energies at that point here. And then step 3 here is that then we apply conservation of mechanical energy to solve for the appropriate unknown parameters. So what I want to do with this is that I want to go in and I want to set up a couple of examples here. So it's where I apply this process here. So let's call this example 1. And what we're going to be doing here is that we're going to be dropping a ball with no air resistance. So I gotta have some information here. So what am I going to do here? Well, I'm going to imagine that I have a ball that I'm going to drop. And from this process here, I'm going to guess here that I'm going to say that what I know about this is that I know that, and I'm going to call this state 1. And that what happens here is that I'm going to start at rest, and I'm going to say that this guy starts off with some height which is not equal to 0. So in this problem, I have this scenario. So now what do I do here? What do I know about this thing? Well, I asked, what are the forces acting on this system here? Well, one of the things that I see here is that this, you know what? I made a mistake here. Let me redraw this. And my mistake here is that I have to identify Earth. So in my system here, what I'm going to do is that I'm going to include the Earth. And inside this Earth, if I include the Earth in the system, then inside my system, I can define the force of gravity here. So when I look at this thing, then this allows me to then state that if I have the force of gravity, and that's the only force that's in the system, then total mechanical energy is conserved. So in other words, I can say here is that because there is no external works, then that tells me here that the change in mechanical energy is 0. And therefore, the mechanical energy at 1 must be the same as the mechanical energy at 2, and this has to remain a constant. So now, if I look at this thing and it starts at y1, and I'm going to define y2 to be 0, I could then have two pictures. So this is just the setup for the picture, but now let's look at what actually happens here. So now that we've formalized our process, how do we set up the energy equation to determine the speed of the ball just before hitting the ground? So then here I go. I start with my process and I say, this is my ball. And right before it hits the ground, it's going to be right here. And what I imagine is something like this. This ball starts off with a known energy. This is a known energy. Why is it known? Because I know that V1 is 0, and I know the initial height is Y1. And so as this ball falls, our goal here is to predict what is the velocity at this point. So when I look at that, I don't know the velocity, but I do know that at the ground, this thing is 0. So this now becomes my energy 2, which is my unknown energy. Again, why is that? We don't know the speed here, but we do know what the height is right there. So what does the bar diagram tell us here? As the ball falls, what we're seeing here is that the ball is going through a series of states. So from my bar diagram, so now if I look at my bar diagram, I look at the total energy of the system. Let's say that this is the total energy of the system. And all I know is that this energy is a constant. And that constant cannot change. So we know that this quantity has to be a constant. And we know that because there was no external work. The only work was the work of gravity, which allows us to define a potential function. So now I'm going to imagine that I have a state 1. So if I look at state 1, I see here that all of this energy here has to be in the form of gravitational potential energy. Because we see that the ball starts with 0 kinetic energy. So according to conservation of energy, this ball now continues to fall. And as it falls, what you're seeing here is that the height of the ball is getting lower here. So as the ball falls, what are you seeing? You're seeing that the height of the ball is actually decreasing. And the way we see this here is that we're seeing that the potential energy is getting smaller and smaller. Then that means I am converting potential energy into kinetic energy. And then at one point, it reaches the ground. And this is what we call K2. And at the very bottom here, we know that this is the gravitational potential energy at the bottom is 0. So when I look at my bar diagram, this is what this information is telling me. But for my problem, we only care about energy 2 and 1. These guys right here, we do not account for and do not care about them, which tells us that we only care about the endpoints. So then I use conservation of energy now. So now if I apply mechanical energy conservation, from the bar diagram, I know that I have energy 1, which is a completely known energy. And then I compare that to energy 2, which is an unknown energy. And so then I start to identify what happens at energy state. From my bar diagram, you could see here that I'm going to get K1 plus UG1. And then at energy 2, I could write this as K2 plus UG2. But I didn't have to draw this guy because we already knew that that was 0. And we knew that this was 0. So my bar diagram really tells me that I could have gone directly to this guy right here. So now this equation sets up the conditions in order for me to solve for the speed at the bottom. So then I use mgy1 is going to be 1/2 mv2 squared. And we're seeing here is that conservation of mechanical energy sets up the equation to solve for V2. And that's the power of conservation of mechanical energy. So if you can get this picture here, it's a very, very powerful picture. And it's definitely easier than using the work energy theorem. Now let's do one more that involves a spring here. So this will then be example 2. And in this case, we're going to have a cart. How did I write this before? Okay. We're going to have a cart compressing a spring. Now, let's look at this thing in a couple of ways. So the first thing that I want to do here is that what we're going to do here is that we're going to suppose a cart starts at some height. on an incline. Then it collides with a spring later on. And then we're going to ask the question, how much does the spring compress? So I could imagine that I have a picture like this. Now note, I didn't write this enough words to describe it, but the picture should do that. So I imagine that I have an incline. And it's a frictionless incline. So if I look at my cart, I'm going to say that I have a cart here. And let's say that this cart at this point here starts from rest. So in other words, I know that V1 is equal to 0 here. Now, when I'm looking at this thing here, I imagine that this is a frictionless surface. So there's no frictional force at all. At the very end of this thing, let's not do this, let's do this right here. I have a spring that then is going to be compressed. So what do I know about this? So here I go. So there's really two situations that we need to consider. One situation, I look at this guy and I say, what do I know about this state 1? So I'm going to call this state 1. Then I'm going to have an intermediate state 2. And then I'm going to call this guy over here. Believe it or not, this is going to be state 2 as well. And then there's going to be a state 3 because there's going to be a compression. In other words, at some point, I have to compress the spring here. And as I compress it, I'm going to call this state 3. So when I look at this system, what do I see here? One, I have the Earth down here. So if I take my system and I include Earth, then the only force acting here is the force of gravity. The force of gravity will not change the mechanical energy of the system. Now, if I look at this guy right here at state 3, what I'm going to see is that in this system, I'm going to have a spring force. What do I know about this spring force? Spring forces do not change the mechanical energy of the system. So now let's draw a bar diagram for this system. So if I look at a bar diagram, here's what I'm going to find. I'm going to start off with a system here that has a constant mechanical energy because we've already agreed that there's no external work. Therefore, the change in mechanical energy has to be 0, which then means the mechanical energy at any state, let's call this 1, no matter how many states I have, that this mechanical energy, right? Let me be a little bit more careful. That this mechanical energy has to be the same no matter what state I'm looking at. all of those energies have to be the same. So now this is telling me that this mechanical energy, regardless of what I look at, will always be the same. So here I go. This cart starts off at some height y1, where we're going to say that this guy is a known height. So then the total mechanical energy, again, this has to remain a constant. The total mechanical energy tells me that at this point, I only have the force of gravity at this point right there. The cart starts at rest, so therefore kinetic energy is zero. There is no spring system here, so the spring potential energy is zero here. It contributes nothing to the energy of the cart. Now, when I look at this thing, this cart is going to go all the way down. And as it goes all the way down, you're going to see that now all of a sudden, all of the energy goes down and you get to the point where this height here is now zero. So that means at this point here, the kinetic energy at 2, all of the energy has been converted into kinetic energy. In other words, the gravitational potential there is zero. Now note, I'm not going to write the spring because the spring does not enter the system. Now look what happens. So the cart gets all the way down to right here. And now it's moving at this point. And what's it going to do here is it's now going to start to interact with the spring. So state 2 at the bottom of the incline is exactly the same state at right before it hits the spring. So then after it compresses the spring here, what I would expect then that all of the spring potential at 3 here, because we expect that at V3 here will be 0 when you have max compression. And this max compression we're going to call X3. So when I look at this thing, you can see that the spring potential, the gravitational potential at 3 is 0. Why? Because the height is 0. And also, there is no kinetic energy at 3 because it has stopped moving. So when I look at this whole process, this is how energy keeps, changing as it goes all along. So now I'm going to redraw my picture again. Okay, I'm going to copy this and I want to redraw my picture. Oh no, let's not do that. So I want to redraw my picture for a better, cleaner diagram. Maybe I shouldn't say the word better. I should say for an easier, cleaner diagram. So now let me add this guy in here. So now I'm going to modify this. I'm going to say that we already know that we have this. I don't care about the state 2. I don't care about them at all. All I care about is what happened to the compression here. So now I'm going to get rid of all of this and I'm going to bring this guy down. we've already identified that we're going to get a compressed car. So this is my state 1. This is my state 3 here. So when I look at this thing, the only thing that matters to me is that now I have let me move this here a little bit. This point was x equal to 0. This point, this distance right here, is going to be my compression x3. So when I look at my cart, what do I see? I see that my cart now has stopped moving here. I get maximum compression here. So now I look at my energies. So what do I know about my energy state 1? Well, I know that this guy here has a height of y1, so then energy 1 is my known energy state. When I look at energy state 3 here, this energy 3 is my unknown energy state. Why is it that I don't know? I know that the speed at 3 is 0. I know that the height is 0, but I don't know what this compression distance is. So now I can apply conservation of mechanical energy, and it goes like this. So now the bar diagram shows that if I look at energy state 1, again, remember, all of the mechanical energy must be a constant. So then, if that's my constant here, then from what we've already did here, that means that I have 0 kinetic energy at 1, and I have only gravitational potential at this point at 1. When I get all the way to the energy state at 3, I see here is that all of this energy state is now in the form of spring potential energy, because at this state, we see that the kinetic energy is 0, and we also see that the gravitational potential here is 0 because y3 is 0. So now I can apply conservation of mechanical energy. So then the mechanical energy at 1 must equal the mechanical energy at 3. And then from my diagram, you could see here is that I could immediately write, I could write K1. I really didn't, because we already see picture-wise that this is 0. That's what our bar diagram is telling us. And then when I look at mechanical energy 3, I could write my kinetic energy, and I could write my gravitational potential energy there. But we already knew that these guys were 0. So the only thing that really counts is the spring potential energy. So if I had drawn a bar diagram, I could immediately have gone to this guy right here. And then if I write the equation out, this will then be mg y1 is going to be 1/2 k, the compression x squared. This is the equation. So this sets up the condition to solve for x3.